look and teach our presentation that
Mm-hmm.
tomorrow.
Great.
So thank you, and we look forward to that.
Thank you. Thank you, Sasha. Thanks for coming, everyone. So this will be a crash course in fluorescence and photochemistry. This is kind of the behind the scenes going towards those applications. And the way I see teaching sometimes is as if I'm teaching a surf lesson. So I'll be sending waves. Some you'll get that'll bring you forwards. Some will be like, this is a baby wave. What are you doing? Some are going to be way too high. So hopefully you can get back up, and I'll keep on spewing information for 2 hours. The pace is quick because I tend to go on tangents, and I know that I have a lot of stuff prepared. So let's get right to it. Come on. Okay, so the slides are available here, the PDF, or if you type it correctly here. So let's get started. No, it's all good. Thank you. Yeah, you figured it out. Thank you. All good. Yeah, the TMI is connected. Okay. Thank you very much. All right. So let's start. Light is an electromagnetic wave. If it oscillates quickly, the wavelength is short, the energy is high. The relationship for the energy of a photon is proportional to frequency, proportional to wave number, inversely proportional to wavelength. Chemists, we like wavelengths because experimentally it makes sense. That's how they're separated. Physicists tend to like wave numbers or electron volts. But yeah, light is an electromagnetic wave. The electric part is the important part. If you stretch a conductive polymer around, so this is conductive polymer here, you can absorb wavelengths that go in one direction. And then if you force the polymer to be stretched, the conductive polymer to be stretched in the other way, then you can block the light. So that's how those polarizers work, right? So they absorb light that is oscillating in one direction. And if you switch it, then you don't have light going through. This is how LCD screens work. Probably this screen as well. It's just allowing pixels, green, red, and blue, to go through or not with liquid crystals that change the polarization of the light. So that's light for you. Light is of course, more than just visible light. We have all the way from gamma rays to radio waves. There could be wavelengths that are 60 kilometers long that have a bunch of energy. We just don't have antennas yet. But at some point we might discover other worlds with those crazy long wavelengths. But right now, these are the ones that we have detectors for, and then we have sources for, just to calibrate CC bond strength around 90 kcals in the UV. CH bond strength is around here in the near or mid infrared. And your microwave, as you heat up microwaves, what you're doing is you're rotating water molecules that are colliding each other with molecules, and that's why they heat up. And that's why also frozen things don't heat up very well, because they're frozen and they don't rotate. So make your microwave work a bit better. Try to crack it up, put a little bit of sprinkled water around it, and those water molecules will initiate those reactions. But as chemists, we use a lot of these wavelengths as spectroscopists. So, of course, NMR, IR, X-rays. But today we're going to be talking about people's favorite, which is the visible. A lot of those slides will have French all throughout, because on the train ride I was trying to translate and I missed a bunch. But that's okay. So it's our favorite for a reason, because the sun at the surface is 5,500 Kelvin or so, and that's black body radiation of the sun emits in the visible. So you've heard about the ultraviolet catastrophe, which is Planck resolved by, saying that light is quantized, and basically that gives you the emission spectrum of light. We see visible light over here. There's UVA. UVA light is the light that we can't see, but it goes inside. So UVA is not blocked by windows. UVB is blocked by windows, and UVC is blocked by the ozone layer. So fortunately, we had a great agreement that we don't do CFCs anymore, chlorofluorocarbons, which was a great catalyst to destroy the ozone. And the world got together and banned some bad things that were in the air. And hopefully we'll be able to do the same thing for something else, which is global warming problem. So we have energy in, the energy that wants to go out, again, black body radiation. The Earth is an average of 15 degrees Celsius, although right now in Montreal it's minus 15. But on average, it's emitting in the infrared. So rather than being 5,000 Kelvin at the surface, we're at 15. So we're emitting in the mid-infrared. And that turns out that CO2, if I'm carbon, I have two oxygens, the symmetric stretching doesn't absorb. That's not the problem. The problem is this one. So the asymmetric stretching of CO2 is absorbing the light that should go outside. So basically the earth is warming up. And if I have, for example, my son is, making a fever, so it's like 39 degrees Celsius, I'm going to put him in bubble wrap and then tape him all up. That's probably not the greatest idea, but that's basically what we're doing with the CO2 in the air. The CO2 is absorbing the light that should be going outside. And that's the mechanism by which global warming happens. Yeah. Spectroscopy. All right. The basics in terms of light matter interaction. Every time light changes refractive index, it changes speed. The refractive index of something is the fraction by which the light is slowed down. So water's refractive index is 1.33. And so that means it goes, instead of going 3 times 10 to the 8 meters per second, it goes 3 times 10 to the 8 divided by 1.33. And every time the light changes refractive index, there's a fraction that bounces back. And the formula to calculate it, if you're going at the right angle here, it would be this Fresnel equation. And I really like this equation because it explains so many things. It explains why we can see each other, because there's a change in refractive index between you and the air. So there's a fraction of the light that bounces back. There's a fraction of light that goes in your skin. It bounces around and changes direction at every refractive index. It also explains why ice is transparent and snow is white, because snow is white because there's a change in refractive index between every crystal of ice. So it explains also why Teflon is white and PMMA, polymethyl methacrylate, is transparent. Does anyone know why that would be? Why is Teflon white and polymethyl methacrylate transparent? It's related to this one. The same molecules, right? So it's just that happens. What happened is PMMA is an amorphous polymer, so there's no change in refractive index. It's the same refractive index all over, but Teflon has crystalline regions, amorphous regions, crystalline regions, and those changing in refractive index make it so that there's light that bounces back every time. So Teflon is extremely white, and the reason is because you have changes in refractive index within the material. So this formula explains a bunch of stuff. It also explains this little demonstration. I'm going to try. I'm going to take paper and pour some water on it. And basically, paper is a bunch of cellulose with air. It's high quality paper, so it might take a while to absorb. It should look darker as the water is absorbed. It is pretty good paper. It would work really well with toilet paper. I think you've seen water and paper before. Let me show on Zoom. Does that work? Let's try it. Yeah, I think your paper is too good. Good. It can work? No. Normally you can see right through it, but if it's too, the paper's too good quality, you can't really see through. I have to really work on the water. But I'll sacrifice myself. So basically, if you, this is less good quality than your paper. So if you wet yourself, so now I just wet myself with water. And so it looks darker. Why does it look darker? Because my fibers are at an interface of air and fiber, air and fiber, air and fiber. Now, if I put water, there's a smaller refractive index change. And that smaller refractive index change makes it so that there's less light that bounces back. And so it looks darker. And so it has more time to bounce around in the tissue for the fabric. And so it has more time to get absorbed by the pigments. And that's why it looks dark. That's why if you're working with wood, put some oil, it looks darker, it looks better because it changes the refractive index. Okay, explain a bunch of things. Now, let's talk about colors. Why is an apple red? I have 3 kids and they ask questions. And so I'll explain it as if I was both the child and the adult. So why is an apple red? Well, it's red because it bounces red light back. But why does it bounce red light back? Well, because there's a change of refractive index between the apple and the air. So that's why the red light bounces back. Why don't the other colors bounce back? All right. So because the blue and the green are absorbed and the red light is not absorbed. And that's why it bounces back. So an apple is red because it absorbs green and blue light, but doesn't absorb red. So but then why does it absorb green and blue light and not red? Well, it's because it has pigments inside. And those pigments are like this one, cyanidin. And that molecule, if you take the UV vis spectrum of it, you see that it absorbs in the 450 nanometer region, in the 500 nanometer region, but it doesn't absorb in the 600 red nanometer region. So that's why this molecule here looks red. And a leaf, for example, would look green because it has chlorophyll, manganese porphyrin, and that manganese porphyrin has thorium Q band, which absorbs blue and red light, but doesn't absorb green light. But then why are plants green if the sunlight's maximum at green? Like that makes no sense, right? Have you guys asked yourself that question? Like sunlight emits the most amount of energy in the green, and the plants are like, I'm not going to take that light. Does anybody need to know? The answer happened 500 million years ago. So 500 million years ago, there's the great oxidation event. And there were bacteria, cyanobacteria, all over the earth. Well, in the oceans. And those cyanobacteria had an absorption spectrum that looked like this. So they're really great at taking those photons. But those cyanobacteria, their poop was oxygen. So they just excreted oxygen. And in the greatest titration of the history of the world, that oxygen oxidized iron 2 to iron 3 to make rust. Eventually, those bacteria were generating so much oxygen that they completely, rusted out the ocean, which created a bunch of oxygen in the air, which was toxic to basically everything. Oxygen is a very active gas. And it killed most of them, except for a few algae that were picking up the leftover light in the red and the blue regions. So they had developed porphyrins to absorb the red and the blue regions. And those are the ones that evolved eventually into plants. So that's why plants don't absorb the maximum wavelength of light, because they were second place. But now they're first. So absorption spectroscopy is obviously a very useful tool. You take a blank, you put it in, you measure how much light hits your detector with your blank, then you put in your sample. I0 over I. I over I0. I is the amount of light hitting your detector per sample over I0. And then we don't typically go with percent transmission. We go in terms of absorption. And the reason is simply that absorption is proportional to concentration. So that's why we have this weird definition in absorption where we take a minus log and then we have no units. Some people put AU as in arbitrary units maybe, or absorption units. They're actually just no units because it's a log. So you can't have units in a log. But if you do your calibration correctly, you can get the mole absorption coefficient, figure out the concentration. So of course it's useful in a bunch of things, but if you have multiple things that absorb at the same time, you have to separate them. Okay, so baby wave, HPLC, how you separate compounds, and then you integrate that and quantify your compounds. Even a TLC is a UV vis basically, right? So you're exciting at 254. There's manganese doped zinc silicate in there that emits light. And if your compound happens to absorb those photons, they won't get to your manganese doped zinc silicate, so they won't fluoresce. So that dark spot is an absorption experiment. How it works is fairly simple. You just need a light source, a way to separate that light source, a way to scan those wavelengths. So prism, here's the French, and a way to detect it. Normally it's just a photodiode. You're basically creating current with light, so just like a photovoltaic cell would. But I'm going to explain to you how a PMT works, a photomultiplier tube, which is more precise, more sensitive. Basically, a photomultiplier tube, if I draw on there, this is a photocathode. So Einstein got his Nobel Prize for the photoelectric effect, which is the conversion of light to electrons. And so that photocathode does that. So it absorbs the light, transfers an electron. This whole thing is under vacuum, right? Electrons don't like the air. So that electron is accelerated towards this focusing electrode here, which is positive. But the next one is even more positive, and even more positive until you can get up to 1,000 volts difference between all your photocathode and your anode. So basically, those electrons just get amplified. So that electron is accelerated. It makes a splash of other electrons, which are accelerated. It splashes to more electrons, and then eventually you'll have a current. And that current goes through resistance, and you have a voltage. So that's how, most of spectroscopy is just a voltage versus an energy. And that's what it is here. So you have a voltage versus a wavelength. So what your detector sees is a measure of, let's say, I0. So this is the amount of light that hits your detector for a certain wavelength. And then you might put in your sample and it absorbs less, right? So you have, for example, something like this, and then it absorbs about half, and then it absorbs everything down here. So this would be now your So then your computer does minus log I over I0, and it'll give you something that looks like this. Oops, you should go to 0. So if you're absorbing at 0.3, that means you're absorbing 50% of the light. If you're absorbing 2, that means you're absorbing 99% of the light. You're really pushing it in terms of what you can detect. And there are a lot of reasons why you shouldn't go above 2, and I'll give you very quickly some of them. So this is usually these pitfalls that you see all the time. If you start doing quantifications above 2 and you have electronic noise or you have stray light coming in, you have deviation because your I0 measures the signal when there shouldn't be. Also, something that's very common in nanoparticle science and material science. I'm not citing who did this, but you see this a lot, where there's a beautiful 0 that matches, like all the curves match to 0. This is obviously doctorate data. This is not true because those particles scatter light. So there's going to be some residual absorption at 700 nanometers, and that's fine. That's information. But just people don't like it because that means you have some insoluble impurities in there, and that normally people will just try to force it there and say it looks really nice, but it can't. This isn't correct. Another thing that's often problematic is when you're doing DNA stuff, you're trying to measure things in the 230 to 260 nanometer wavelengths. You can't see that. It's very difficult to know if something absorbs at those regions, right? So this is from a paper where you have a negative absorbance. Obviously, there's a problem. You can't have a negative absorbance unless your sample is, radioactive and glowing. And in this case, what happened is that their blank buffer had EDTA. They purified it. The EDTA left, and so now your sample didn't have EDTA, which absorbed. So your baseline was absorbing more than your sample. That's why you have a negative absorbance. But that comes in. It's important to know the intricacies of UV vis. Even though you've grown up on it, it sounds very simple. But I have my little pet peeves about how people measure UV vis. Okay. Again, why an apple is red? An apple is red because it reflects red light, because there's a change in refractive index, because it absorbs green and blue light, because it has pigments that absorb that green and blue light. Why does it absorb green and blue light? Well, because that molecule is in the ground state here, and it can absorb to different levels, and it can't absorb here. Why can it absorb there and there? Why can it absorb green and red, blue, not red? Schrödinger's equation. So this is a very important equation. People have had it tattooed on themselves. It's less popular in popular culture than E equals MC squared, but it's infinitely more useful. It predicts a bunch of things, and so it might not be appropriate, but to show you. Okay, so let's do a little Schrödinger equation. We'll solve the Schrödinger equation for a particle in a box. Especially you mind. For the people on Zoom, I'm going to go and basically swing a rope around and try to solve equations with it. Sorry about that. Okay. Okay, so particle in a box is the first thing you do when you solve what is the equation. Basically, you had a box of length L. You had the first, second, and third solution going up. If the box gets wider, those levels go down and get closer. And that's why theta carry each at 11 double bonds in the from green looks orange. And then if you broke our 11 double bonds to 3 double bonds, it becomes transparent, so that's other full bond. Let's solve the equation. So if you have the whole bond type, you might want to get a rubber on it. Yeah. So let's solve it for a small L like this. So this is the first solution. That's like here. So let's go. That the first solution, that's the easiest one. I don't have to work very hard. But then I've worked pretty hard to get the second solution. So that spectroscopy will be taking that electron going from N1 to N2. It can be easier if I lengthen in the box. But I'm going to go, this is much easier. But lower in energy, and if I goes, you can do so the first solution, and then be able to get the second solution. Basically, the solution of the Schrödinger equation are just increasing the number of nodes in the solution. So you're increasing the number of nodes. So here you have 0 node, 1 node, 2. So that's for a particle in a 1D box, which is not realistic. Atoms are not one-dimensional. So for atoms, when you solve Schrödinger's equation, Rather than just having one quantum number, you need to have four, N, L, M, L, M, S. These are numbers you've learned in high school. And these numbers represent orbitals. The 1s orbital is the easiest. No nodes. Everyone wants to live in the 1s orbital. That's the lowest energy one. That's the downtown penthouse. Everyone wants to live there, but there's only 2 electrons that can live, right? Then once that penthouse is occupied, then you got to go to the 2s orbital, and then you have to have one node. And that one node happens to be a spherical node rather than just a point node as the string experiment. It's a spherical node. And then you have 3s, which has 2 spherical nodes, 4s, and so on, right? So you're just increasing the number of nodes in there. And what these are, these, let's say, areas, they are solutions to this equation here. It's actually a triple derivative, and basically if you have a mathematical function, the wave function that describes where you can find an electron, more or less, you can say, well, let's get this equation to be equals to 0.9. So that means that inside this sphere, I have a 90% probability of finding an electron. So that's basically how I interpret orbitals. It's just the probability of finding something inside this sphere. If you're solving for 0.5, it's going to be smaller. If you're solving for 0.99, it's going to be bigger. If you're solving for 1, it's going to be the universe entirely because you can't completely contain an electron. So that's 1s, 2s, 3s. If you go then to p, well, what you're doing is you're taking your ball of pizza dough, you're cutting it once, one node, so one planar node from S to P, and then one more cut for D, and that costs energy, right? So the 1s orbital is more stable than the 2P, which is more stable than the 3D, and then you can have both of them together. So for a 3P orbital, we have both a spherical node and a planar node. And that's basically, you build up the periodic table this way, right? So that's all it is. It's just spherical and planar nodes all the way down. Then you combine them together and you make molecules. So when you have benzene, you have a bunch of p orbitals that interact either in phase, that's lower energy, or out of phase, that's higher energy. So anytime you combine orbitals, you can make something good, but you always make something worse. The way I sometimes say is like, you can live your life not interacting with anybody. You won't have any bad feelings, but you won't have any good feelings. The other way to say it is like, the person that could hurt me the most is my wife. So we're very close. We have a good overlap. We want to populate those bonding orbitals, but those antibodies are very high, right? So that's why, those orbitals are very high energy and you don't want to live those. But you don't want to be completely non-bonding. You still want to interact with the world. But if you have somebody who's not, like, if I'm walking downtown, someone screams at me, that should not bother me. Like, that person has no overlap with me. Is like, whatever, right? So I think you have to decide who those people are. Who do you let into your bonding orbitals? Who do you let into your anti-bonding orbitals? Sometimes it's good to get excited as well. Okay. All right. So once we solve Schrodinger's equation, you can solve anything, right? You can know everything about the system. You can know about the thermodynamics. You can predict the kinetics by calculating barriers. But this is spectroscopy, and so we're going to be talking about light matter interactions. You can solve all the molecular orbitals, and you can figure out how much energy or which photon would it take to fully ionize the molecule. And when you do XPS spectroscopy, I don't know if anyone does XPS, you're just fully ionizing the molecule with a very high energy photon and figuring out how much kinetic energy it has, and that tells you what the binding energy of that orbital is. You can do this with many different geometries now. So you can take a molecule and twist it around and calculate all the energies of all the electrons. And that's going to be, let's say, the surface down here. We'll call this S0. So this is the ground singlet state. That's where most chemistry happens. You're just skating around on this potential energy surface. But as a spectroscopist, I like to go into the S1, the excited state. And then eventually those can somehow recombine. So these are conical intersections. So the excited state is created, and there's a geometry for which both the excited state electronic configuration and the ground state electronic configuration have the same energy. And that's what most molecules do. They absorb light, they just dissipate it as heat. So they'll find one of these funnels and keep on going down. Right? So this is not that exciting. Another one that's a little bit more exciting is this molecule. So this molecule has a double bond somewhere. So you can have a cis and a transform of that molecule. The transform is usually more stable. You can excite with light. So you have light coming in. And then that molecule in solution looks like this. It's not fluorescent because you excite it, it'll go to 90 degrees, it'll go here, and then you'll have cis-trans isomerization going on. So photochemistry is well known to do cis-trans isomerization. If you're able to only excite one of those, you can keep on doing that trick, and eventually you may be able to populate only the cis. If you can find a wavelength that waits you excite only the transform, you'll keep on doing this excited state, and eventually you'll just funnel your way to cis. That's a way photochemists like to make cis double bonds. It's also useful in terms of DNA staining. So if you look at, forget which nucleus green, I don't know, I have no idea what molecule this is, but it intercalates in DNA. When it intercalates in DNA, it can't rotate anymore. It can't do this cis-trans isomerization. So now it's stuck. Now it basically doesn't have access to this rotation. And so now it has no choice but to flex. So basically you can stain the nucleus using this trick. So this is just DNA that I put in the vial and it glows. And I think I had let's see. Okay. I had a little video, but okay, let's go back to basics, orbitals. So when you have a molecule, that molecule is in the ground state. That ground state is occupied. There's a bunch of other ones that are occupied in the ground state, and all the LUMO plus one are empty. If you have light coming in, you can create an excited state. So basically, you're just taking an electron and putting it up there. It doesn't have to go to the LUMO. It could go to LUMO plus one. It could go HOMO minus one to LUMO plus seven. Doesn't really matter. But quickly, if you're in solution, that molecule will go to the first singlet excited state. So one electron in the HOMO, one electron in the LUMO. Fluorescence, which I just showed you, is just the return. So you'll have fluorescence here. Call you back. Oops. That's supposed to be an L. You're probably getting COVID nightmares from people scribbling on the keypad. And then this is quick, right? So this is very quick. So the absorption is extremely quick. The fluorescence is also quick. But sometimes you can go to the triplet, which is just changing the spin. If you do photochemistry, you want to typically go to the triplet because you can't simply go down here because every electron needs its own address, right? Pauli exclusion principle. Every electron needs to have N, L, ML, MS, one mailing address, and no one else can have it. And that means that this electron cannot go back down here because that would mean it would have the same spin in the same orbital, and that's not allowed. I have no idea why, but those are the rules we have to follow. So what happens is when you have a triplet, that triplet excited state now is going to live much longer. So now it has time to do photochemistry. That's important because the singlet excited state is too reactive. For example, for all those who measure fluorescence, you typically don't degas things. You don't remove oxygen from your solution. Although that singlet excited state would react with oxygen in a shot. It's just too short-lived. That oxygen is millimolar concentration. It just doesn't have time, right? But if you're doing photochemistry, that triplet excited state now has time to interact with oxygen. So that's why a lot of photochemistry is oxygen dependent because triplets can react with that oxygen. I'm sure every one of you have seen this probably too many times, but I'll still go through it. That's the Jablonski diagram. So a molecule is in the ground state, S0. That S0 has the electronic configuration that is, for example, HOMO, LUMO, right? So LUMO is empty, HOMO is filled. And then the absorption process is extremely, extremely quick. This happens in 1 femtosecond. 1 femtosecond is to 20 seconds, as 20 seconds is to the age of the universe. So the thing that gives things color is that fast. It's extremely fast. And so basically the time it takes for light to cross an atom, or a fraction of an atom. But very quickly, that excited state will, especially if you're in the solvent, will do vibrational relaxation, internal conversion, and go to the S1. So the S1 is 1 electron in the HOMO and 1 electron in the LUMO set. Opposite spins. So you're still in the singlet state, and that can keep on going. That can find those funnels, those conical intersections, and just dissipate heat. That's what most molecules do, right? In this room, things are not just slowly degrading and reacting with light. They're just kind of there. They absorb light, electrons spin. It just releases heat. I have this theory that everything in the 1970s was kind of brownish because that's where it would go anyways. So plastics were not that good, right? They would yellow with time. They would photo yellow. So like, let's just paint it brown to start with because we know that the plastics are not getting it. So that's my theory. I'm not sure if it's true. So fluorescence is much slower. So absorption is femtoseconds. This process is picoseconds, 10 to the minus 12. Fluorescence is 9 nanoseconds. 1 nanosecond is the amount of time it takes for light to travel a foot. So just 1 foot of light is a nanosecond. So I'm seeing you guys 10 nanoseconds in the past. And then the triplet is to have both those electrons in the same spin. And then you can start seeing that doing chemistry. What I've shown you so far is only photophysics. We haven't broken bonds yet. And we won't break bonds for a bit. This is another Jablonski diagram that's a little more complicated, but it helps explain the Stokes shift. The Stokes shift is the shift in the lambda max of the absorption and the fluorescence. That's important, especially if you're doing microscopy or things like that, because if you're doing microscopy with fluorescence, you need to excite your dye, but then you need to measure your dye, and you're sending way more light into the system than you're getting out. So you need to wait. You need a way to filter out those photons that you're exciting, right? And that Stokes shift is what allows you to do that. The Stokes shift is like you can excite your molecule in the absorption band, there's a shift, and you have a filter that is measured with fluorescence. So I'll try to explain this to you. That's going to be a wave that some of you are like, man, never mind. Or some of you will be like, well, that makes sense. Okay, so now we have molecular coordinates on the x-axis, which is really 3n minus 6 for the number of atoms in your molecule. It's a multidimensional thing. And there's a minimum. There's a geometry that the molecule likes to be, and it keeps on vibrating at that V0, so that's first vibrational level. Most molecules are there. They're at S0, V0. So that's most molecules. They're down here. And then the absorption process is extremely fast, so fast that we assume that the nuclei don't move. Those nuclei are frozen because the light absorption is so fast. That's the Frank-Condon principle. So light is absorbed. That excited state is so fast that the nuclei have no idea what's going on. But then it has too much energy, and it will blow through that energy very quickly, like someone who wins the lottery and has too many friends. So that money, that energy is going to be dissipated really quickly. Electrons are like doing parkour, so they get scared of heights a little bit. So if there's a small gap between S2 and S1, that's fine. They'll just jump down those stairs very easily. Going from S1 to S0, that's a big drop. So you got to think about it a little bit. So that's why those electrons are kind of waiting around and seeing what's going to happen. And for those internal conversions to happen from S2 to S1, you need to have a geometry that is thermally accessible, where both the S2 is basically, for example, HOMO minus 1, LUMO. So this electronic configuration, and the S1, which is HOMO, LUMO, 1 electron each, you need to find a geometry where both these configurations have the same energy. Those are your funnels that allow you to go from one state to the other. They call these adiabatic transitions. So the S2 goes to the S1, and that's easy if they're close in energy. That point will be important later on when we're designing photocatalysts. The singlet to triplet gap, if it's a big gap, it'll take time to go. If the singlet triplet gap is small, then it can go much more quickly. And then I'm going to explain the Stokes shift for you guys. So the Stokes shift is explained by looking at the geometry or the electronic configuration of S1. Most molecules that fluoresce have pi to pi star excited state. So the HOMO would be a pi bonding orbital, and this would be a pi star antibonding orbital. That pi star is antibonding, which is going to weaken the structure of the molecule. So that's why the geometry that is optimal for S1 is more relaxed than the S0. So S0, that molecule is all buttoned up. S1, a little disheveled, a little bit more let loose. And that small shift is actually the reason for the Stokes shift. So molecules that are kind of floppy already, you're looking at it like, okay, it's going to be moving quite a bit. You can kind of guess what type of Stokes shift you're expecting for the molecules. Most molecules have a Stokes shift, obviously, but I'll show you one that is very buttoned up, and that's anthracene. So anthracene is a nice molecule because you can see all the details. Basically, it's the analogy I give here is everyone has abs. Most people, we don't see them. So anthracene, we see its abs. So anthracene has an absorption spectrum that is always starting from F0 and also the V0. When I say V0, it's like just the lowest vibrational state. When you're doing IR, you're going from V0 to V1. So IR is just these small transitions. When you're measuring infrared, you're going from V0 to V1. When you're doing UV vis, you're doing both. You're doing electron jumps and vibrational jumps. Okay, so let's look at what's going on here. So look at this Stokes shift. This molecule is rigid. There is nothing going on in that excited state. So that molecule is, just absorbing light, going straight up, and then going back down like a soldier, and emitting light. You can look at the nice vibrations here. These are vibrational modes. So you can start to assign what those transitions are. Again, this is happening for all molecules. It's just that this one, we can see all the bands specifically. So this transition here is S0, V0, which most molecules start with. And then it goes to S1, first excited state, and V0. Oops. There we go. And then the next one would be to V1, V2, V3, V4. Eventually, if you're at V5, like the molecule vibrates a bit too much, and then there's no overlap between the geometries. The mole absorption coefficient shrinks down, and that's why you have these kind of shapes. Fluorescence is always from S1 V0, so it always starts from here because of Kasha's rule. I don't think I said Kasha before, but Kasha came up with this. It's a guy from Florida in the 1950s. Came up with the concept that if you excite a molecule, no matter where you excite it, you'll go back down to S1 V0. Then the molecule has nanoseconds now to figure out what it's going to do. Is it going to keep on going down, emitting heat, or is it going to emit light? In this case, it's going to emit light, either going down from V0 to V0, that band here, V0 to V1, V0, V2, V0, V0. So this molecule explains pretty well what's going on in every molecule. It's just we can see details. Okay, let me go into the details of how we measure a fluorescence spectrum. So now this is just a fluorimeter, just as I showed you before. You have a light source, goes through a monochromator, where you're choosing the lambda excitation. And then you have another monochromator that's measuring lambda emission. So rather than having one monochromator like UV vis, you have two. That's basically it. Well, fluorescence is more powerful than UV vis, but it's more complicated. So UV vis is like a really simple, like Windows Movie Maker, but fluorescence is like Pro Tools. You can do a lot more things, but you have to learn the tools properly. One thing is the y-axis is completely arbitrary in fluorescence. In UV vis, it was nice because an absorbance of 2, no matter where you're on the planet, if you did your blank correctly, a UV vis of 2 means that 99% of light is absorbed. If it's 0.3, that means there's 50% of light absorbed. If it have a fluorescence of 10, it means nothing. Some fluorimeters have 1,000,000. Some fluorimeters go to 1,000. Some go to 0.6, and it's completely random. So it becomes difficult to compare results. And that's why fluorescence is tricky to reproduce. And you have to do things very carefully to have results that can be reproduced. Fortunately, we have a concept called fluorescence quantum yield. Fluorescence quantum yield is the amount of light that is emitted for the amount of light that is absorbed. So if a molecule absorbs 100 photons and emits 60 photons, its quantum yield is 0.6. So the fact that there's a quantum in there doesn't mean it's complicated. It's just a fraction of photons absorbed and photons emit, basically. Okay. But fluorescence in theory should be linear with concentration. Fluorescence should be proportional to absorption. And absorption, remember, is epsilon CO. And so fluorescence should be proportional to concentration. So that's good. We can use fluorescence to quantify it. However, I'm sure some of you have seen this. If you start measuring fluorescence for concentrations that keep going up, eventually you have deviations from the linearity. And this is data that I measured myself. The fluorescence goes up and then it actually can go down eventually. So if you have a calibration curve with fluorescence and you're trying to quantify the amount of stuff you have inside, if your value is this and you have 2 points for which the concentration gives that response, it makes no sense, right? Because you have no idea if it's going to be this or this concentration. So that's a huge problem. So there are 3 reasons for this. I'm sure there's many more. One of them is just the screening effect. So if you have concentrations that are too high, eventually your fluorimeter is optimized to measure the fluorescence in the middle of your cuvette. And the middle of your cuvette is just not absorbing photons. So the light is absorbed. So 99% of the light is absorbed in the first little bit. There's basically no photons here. And those photons won't be captured by your detector. So that's a common source of fluorescence decrease. But you can also see fluorescence decrease if you put fluorophores inside of cells or inside of liposomes. If you have molecules that are too concentrated, you can start to see the fluorescence go down. So I had a colleague who was working with liposomes and it put molecules inside and it was measuring the bursting of those liposomes and you can see the fluorescence go up. That's kind of weird. Why it happens is because molecules are jealous. So those fluorescent molecules that are excited, they go in the excited state and then their neighbors are like, hey, what about me? So they start stealing the energy and then that fluorescence quantum yield goes down dramatically. The molecules are notoriously known to do self-quenching. So if you have too many fluorophores, they can interact. I can expand on that if you want, but that's good stuff. And then also you can have a trivial energy transfer. So if you have molecules that have a very small Stokes shift, meaning if you have an absorbance, fluorescence, so you have an absorption, fluorescence. If there's a big overlap between the two, we can have energy transfer that's trivial energy transfer. So molecule can emit light, and instead of reaching the detector, it can just be reabsorbed. So that's a very common problem as well, especially for BODP dyes or things that are very, very rigid. Anthracene, for example. If I go back to the anthracene model here, it's very common not to see this band here because why? Why is this band disappeared? So oftentimes you'll measure the fluorescence of anthracene and it'll look like this, basically. What I just said. So the absorbed light is emitted and those photons are emitted but reabsorbed by a neighbor. So those photons just never make it there. So to measure a proper spectrum of anthracene, you have to be extremely diluted. All right, so these are, so this is now a way to measure fluorescence quantum yield because if you're measuring fluorescence and you want to compare things from one lab to the other, it's good to have a fluorescence quantum yield. So this is how, I forget the name now. So, sorry. Does someone remember the Greek name of that? Phi? Yeah, fine. So phi f. So the quantum yield of fluorescence is related to a standard. So you just basically measure your standard and your fluorescent molecule in the same environment. So basically, you have, for example, now red here would be a fluorescent like this. It has a nice Stokes shift, so that's why it's linear. And then these BODPs, these are molecules that I made. They have a lot of reabsorption, so they're actually quite linear at first, but then they start deviating eventually. But basically, you compare the slope of these things, and then the ratios of the slopes gives you eventually the quantum yield of fluorescence. And now you can say, in these conditions, at this temperature, on this day, at this hour, on this fluorimeter with these slit widths, I can say, okay, this is how this molecule flings. But it becomes difficult to compare even day to day because your fluorimeter might respond slightly differently. The optics might be slightly offset, and so that gives you 10% less fluorescence for whatever reason. So it's very difficult to compare day-to-day experiments with the fluorimeter. So that's why it's good to always have a standard. One standard that's often used. So on our fluorimeter, we always measure the raw amount of water. So the water if you set it at 330, you have a fluorescence. Well, it's not fluorescence, it's a Raman peak. And that one is very easy to always have it right because it's just water. So you just put water in, you measure the Raman spectrum of water, and then you know if that's your internal standard, basically. When you're doing HPLC, you can have an internal standard to know how to correct your y-axis. You can do the same thing with fluorescence just by measuring the Raman of water. That's a common way to do it. Okay, energy levels still. We'll take a short break soon. So it's not all about quantum yield, it's also about molar absorption coefficient. And the product of molar absorption coefficient and quantum yield is called the brightness. And so you have a lot of dyes that emit at different wavelengths and have different brightness. So if you're doing biology and you want to measure things and then sub-nanomolar, you need to have very, very bright dyes or really intense lasers. So if you have a lot of photons coming in, you can have a lot of photons coming in. So the fluorescence community got 2 Nobel Prizes recently. For you guys, it's old, but for me, it's recent. So 2008, Roger Tsien, who passed away actually not too long ago, but so he developed, his students developed green fluorescent protein analog. So green fluorescent protein is a protein that is like a really rigid barrel with molecules that for some reason emit green light in jellyfish. And those molecules, if you isolate the fluorophore in solution, it'll just do cis-trans isomerization. It won't do fluorescence. But in this barrel of beta sheets, it's very rigid and becomes fluorescent. And Roger Tsien and his team was able to make a bunch of different colors in bacteria. And the reason why this is so popular is because biologists really don't like doing chemicals. Like they don't want to play with chemicals. They just want to express a protein and that'll do the trick. But one common criticism is that, well, you have to modify the gene. And also you need to have a huge protein attached to something you're trying to study, which may affect a little bit the properties. So if you're trying to see where this 3 peptide goes into a cell and you have this giant protein attached to it, that might affect the chemistry. Okay, but so that's 2008. 2014 is super resolution. No matter how good you are at focusing light, you'll never get a resolution that's better than lambda over 2-ish, depending on your numerical aperture and a bunch of different things, but it's basically lambda over 2. So if you're trying to study biology with visible light, your resolution at best will be 200 nanometers. That's if everything's working perfect. That's your physical limit. Most of the time, it's less than that. Biology happens on smaller scale than 200, 500 nanometers, right? So if you want to have a better resolution, here's a trick. So STORM, I forget the acronym, but basically you take, you can take a green fluorescent protein that is photoactivated. So it's not fluorescent yet. You can shun blue light, for example. And that blue light will wake up a few molecules, very few. And you can image those single molecules. So fluorescence is one of the only spectroscopy tools that we can study single molecules with. The reason for that is that we can just blast it with a bunch of light. So we can send a whole bunch of light, excite the molecules 1,000,000 times per second, and so it's going to emit 600,000 photons. You can start detecting 600,000 photons. But eventually those molecules will die, because if you have an excited state that goes up and down 1,000,000 times per second, that will die, and that will photobleach. But then you shine another batch of blue light, and then you localize those, and then those will die, and then you shine a bit of more blue light, light up a few, those will die, and then you do a histogram of where those molecules were. And if you know they're single molecules, you know that they're the center of these Gaussian images. So you're still not beating physics. You're not measuring a resolution that's better than lambda over 2. But because you know it's one molecule, it's at the center of this Gaussian. And now you can go from conventional fluorescence to something that's related to biology. The problem with this is that you can't have things that move, right? So you need to have things that are very, very static and you're measuring over time. So the analogy that people use is saying, well, I'm an alien in space trying to understand football. I take a 70 gigapixel image of football. Still don't really understand what's going on, but it gives you an idea of more or less what's going on, right? So that's STORM fluorescence. And it's probably time for a little break. So let's take a 10-ish minute break maybe, and then we'll come back with some photochemistry. Okay. Ready to start again? Okay, so Nathan asked why the S1 geometry is more relaxed, and so let's go over that. So the S0 is HOMO is full, LUMO is empty. S1 would be HOMO with one electron, LUMO with one electron. For most molecules that fluoresce, the excited state would be a pi orbital and a pi star orbital. So, and the pi star excited state. Pi star means anti-bonding, which means that these electrons are not good for bonding things. So the simplest example would be H2. You have the MO diagram for H2, so you have 1s, bonding, anti-bonding. If you have 2 electrons down there, that bond order is 1, that molecule is tight. And then if you have 1 electron up there, all of a sudden that molecule dissociates. So because you've put electrons in the anti-bonding orbital. H2 is an extreme example because that excited state is dissociative. But organic molecules will not suffer that much. They've been through stuff before. They can weather that storm. H2 is a bit of a baby. Okay, so molecules can go in the excited state, but they will still shift in terms of geometry, and that explains part of the Stokes shift. Okay, so I could at this point let's do that. I could keep on going with photochemistry, or I could do a 15-minute detour on what I said I was going to do. I said I was going to talk about hydroxycoumarins. Is anyone interested in hearing about hydroxycoumarin, their fluorescence, and why they're so different? So hydroxy and mercaptocoumarins. Basically, these are fluorescent probes that can light up with different events. Does anyone here work with fluorescent probes or more into photochemistry? So who here worked with fluorescence? Not that many. Okay, so let's do, I guess we have one or two. I would explain how computers work. Okay, so let's skip that. So okay, let's go from photophysics to photochemistry now. And this is again we're starting from the basics of quantum. So I don't think what I'm teaching you now will help you get better yields, but maybe it'll give you a better understanding. Sometimes I say understanding a mechanism or how things work is like understanding how a dishwasher works. You're going to get better results just because you know that it's a spray that turns around and you shouldn't put your glass completely at the corner because the spray doesn't reach there. So this is basically it. I'm explaining to you how a dishwasher works. Hopefully that can come useful sometimes. Okay. So let's do that. So as I said, for photochemistry, if you're dealing with regular organic molecules, you typically want to go to the triplet because the singlet excited state is too short-lived. So all this process here is nanoseconds, and that's not enough time to interact with other molecules. So you need to go to the triplet. How do you go to the triplet? One way is the heavy atom effect. So you put iodines on a fluorescein, all of a sudden the quantum yield of fluorescence drops from 0.92 to 0.11. So it becomes much less fluorescent, but it goes to the triplet 80% of the time. So 80% of the absorbed photons now become triplet excited states. And those triplet excited states can generate singlet oxygen if you care about that. You can do photodynamic therapy. If you want to treat cancer at a surface, you can get access to triplets. Or if you want to do electron transfer or hydrogen atom abstractions, that's also possible. Because that excited state lifetime can be in the microsecond. So microsecond for photochemistry is very long. Okay, so let's compare basically why you would have this. Let's get the transition. The transition was that this is one way with the heavy atom effect. The other way is to make electrons not fear going to the triplet, meaning that you want to have S1 and T1, or at least S1 and some Tn close in energy, right? Because that's how you can have those adiabatic transitions, where you can have a geometry where both electronic configurations have the same energy. That's what's necessary to do these transitions. And that's very difficult to do if there's a big gap between S1 and T1, because there's going to be it's going to be difficult to find those conical intersections between S1 and T1 if there's a big gap. So let's compare the energies, or at least the excited state for ethylene and formaldehyde. We'll see how that behaves. So maybe rather than draw on there, I'll draw on the whiteboard behind me. Hopefully that'll work. Okay. Oh, can you see? No, can't see. Okay, so I have to do again. Good. So you can see that. So let's share the whole screen. We'll try a live demo. If it works. Do I have internet here? Yeah. Would it work? Oh, the demo's not gonna work. I was trying to connect the computer back in Montreal to figure out how to do the calculations for this slide. Fortunately, I did it ahead of time, so we have the results. Guess I need to read those. One more time. You want to connect remotely, AnyDesk is the free software. It works pretty well. Usually. Nope. I even did it on the train. Oh well. Okay, so let's go here. Okay, so now we have the orbital's energy. Well, actually, it's kind of confusing. When you're going from orbital energies to Jablonski diagrams, you have keep on having to change your frame of reference. So that's why even I sometimes trip up with this stuff. So S0 is the energy of the whole molecule. You can't go lower than S0. That's the lowest energy at 0 Kelvin. That molecule has that amount of energy. That's how we define the Jablonski ground state. That excited state now, so if you excite that molecule, you'll change the electronic configuration. You'll take an electron from the HOMO, go to the LUMO. And in this case, it's a pi star excited state. So you basically take an electron from the bonding pi orbital to the anti-bonding pi star orbital. And you can do the same thing with the formaldehyde. Formaldehyde would have this ground state, would also have the p orbitals in phase or out of phase. But on top of that, has a non-bonding orbital. And we typically draw this as a doublet on the oxygen, so a non-bonding doublet. Or if you're from Europe, it's a line. But basically, that doublet looks like this if you calculate it. It doesn't really look like a sp3 orbital. It really looks like two p orbitals that are perpendicular. So that non-bonding orbital is actually higher energy than the pi orbital. And so one way to calibrate yourself to know where a HOMO orbital would be is look at the molecule and say, where would the proton go? So that's the HOMO orbital. The HOMO is where the proton would go. So if I look at formaldehyde, I'm wondering what is the order of the orbitals. If I, put some toluene sulfonic acid on there, that proton is going to go to the carbonyl, not to the double bond. If I take ethylene, I throw some acid on there, then you can do carbocation chemistry because the HOMO orbital is the pi orbital. The other way to calibrate yourself to think about LUMO orbitals is where would an electron go? And so these are, the electron you think would go into pi star, the electron would go into pi star. So it's basically a way to think about HOMO and LUMO orbitals. Where would a proton go? Where would an electron go? And then if you're trying to figure out which projects, what would Jesus do? Right? Now, this is, so we're doing spectroscopy on this ketone. So that ketone goes from S0 to, in this case, the transition from N to pi star is not great. The mole absorption coefficient is going to be in the hundreds. So that means that it doesn't absorb very much. Whereas the transition from pi to pi star is a very allowed transition. For those who like symmetry, it goes from anti-symmetric with inversion to symmetric with inversion. So it goes from Gerad to Ungerad, which is allowed, but from G to U is an allowed transition. So pi to pi star is what you want to do when you have things that are colorful. And generally, if the transition is allowed on the way up, it's going to be allowed on the way down. So that's why fluorophores are pi to pi star transitions. You go from Gerad to Ungerad. That's allowed. And to pi star transitions are not allowed, and those are typically not fluorescent, and they will not even absorb light. So if I take an absorption spectrum of formaldehyde, mainly I'll see this transition, pi to pi star, and there's going to be a tiny, tiny shoulder, that's the N pi star, but you basically don't see it in the UV. So when you're exciting your formaldehyde, what you're going to do is go from the pi to pi star. So you know from S0 to S2. Now this is not the S1, this is the S2. But the S1 and the S2 are close in energy, and those parkouring electrons will find that conical intersection very quickly, and will just go from the N to pi. So that's over in a few picoseconds. Then you have a singlet excited state. It's a biradical. One electron is on the N orbital, one orbital is on the pi star orbital. It happens that because the triplet energy is not so low as this one, and also because there's a T2 that's close in energy, that intersystem crossing is going to be much, much faster. And I realized as I was doing the slide now, the T1 should actually be higher in energy than this one. So I'll finish the thought for why it's fast is because they're close in energy, right? So because they're close in energy, there's a fast intersystem crossing. There's also something in photochemistry called El-Sayed rules. El-Sayed rules say that intersystem crossing will be faster if you change the if you go from pi pi star to n pi star, or from n pi star to pi pi star. So if you change the type of electronic configuration, that usually helps. So intersystem crossing is normally not allowed. So in this case, it's very fast. What the electrons will do is kind of complicated. So we'll have, well, I'll show you first and then I'll explain it. So you'd have a shift in electron that's coupled to a shift in spin. So if I show you this again, so this is actually more allowed than just the spin flips. Spin flips are technically forbidden. So if you just do pen and paper quantum mechanics, you should see, those integrals should be equals to 0. But you can wiggle your way through things, and you can get spin flips if you couple it with another angular momentum shift. So now you have this pi pi star excited state, which is your T2. It's a triplet. The electrons are spin paired, and again, very quickly, that electron is going to go back down here. So now you're ready to do photochemistry findings. After all this, we've done photophysics. Now we're finally ready to do photochemistry. Those ketones are basically like oxygen-centered radicals. Take turbutoxy radicals. What would it do? Same thing as those ketone excited states. So that's basically what they do. They do hydrogen abstraction. They do cleavage. And in photochemistry, we have Norrish type 1, Norrish type 2. So that ketone excited state goes to the triplet. That triplet is basically a biradical. One way to think about it in terms of Lewis structures, which is a shorthand that's incorrect, but it's very useful. So it's a biradical. So it's an oxygen-centered radical, carbon-centered radical. You can push electrons from there. One of the things you can do is you can push that electron down here and take one of those electrons, go here, go there. And now you're left with that radical. You're left with one radical over here, and that's a Norrish type 1. And that's useful for a lot of things. One of them is yellowing paper. So paper yellows because it does Norrish type 1. It makes carboxylic acid, which makes acid. which dehydrates the cellulose, which makes brown. So paper yellows because of light, because you have Norwich type 1 chemistry that does carboxylic acids. And so when you have acid-free paper, is that it will not generate acid. It's not that they used to put acid and that was bad. It's just the light would create acids. It also is useful for nanoparticle synthesis. If you excite this molecule here, this is a photoinitiator from SIBA. And that excited state will cleave by Norwich type 1. And it gives a keto radical. A keto radical is like a caged electron, right? That ketone is basically acetone and a proton and an electron. So it wants to be acetone. And that electron will be given to a lot of things. If you have gold in solution, HAuCl4, that gold 3 plus is going to pick up those electrons. If you keep on shining light, you'll keep on putting electrons in the system. Eventually make gold zero. Gold really likes itself, so it'll make nanoparticles. So that's a photochemical way to make nanoparticles over here. That's Norwich type 1. Norwich type 2 is intramolecular chemistry. So Norwich type 2 would be that excited state is a biradical, and that biradical would do intramolecular hydrogen abstraction. That it makes this biradical. Why doesn't it just snap? Why does it not go like this every single time? Why does this have a lifetime that could do chemistry? Does anyone have any clue? Like, why is it you have two radicals? Why can't they just recombine like this? Yeah, exactly. It's formed from a triplet, so it's still a triplet. So that biradical has the same spin. So those two spins can't click together. That's why you don't have cyclobutane. And I'm a physical organic chemist. I'm bad at physics and bad at organic chemistry, but somehow both together you can kind of manage. So physical organic chemists discovered this reaction, and for a long time, they never took an NMR of this, right? They just injected in the GC and never found out that cyclobutanes are a product because they're just decomposed in the GC for years until some organic chemist took an NMR. I was like, did you see this? But I had no idea. Okay, so basically these compounds can cyclize or they can fragment. This, that. All right, so that's Norwich type 2, and that's also useful. Okay, so now we're going to go into, rather than organic molecules, we're going to try some inorganic molecules a little bit. So one thing that's cool about excited state is that they're both good, well, better electron donors and electron acceptors. That's something that's said a lot of times in photoredox catalysis. So an excited state, this excited state here can react, basically can accept an electron here or can give an electron there. So that electron energy is very high. That electron hole is very low in energy, so it can both give an electron and accept an electron. So let's go through it. And people have gone bonkers with this, like in terms of photoredox catalysis. So this is something that's basically you just take blue light and put it in your flask. You can do this on a large scale with a flow reactor. So this is a photoreactor at Merck. Basically, you just absorb light with some photocatalyst, and that photocatalyst can do electron transfer chemistry that can then kick off this other cycle that you can start seeing 3 different cycles together, and somehow it all works out. And this is old, but you can see that it started in 2008, but it really picked up steam. Photocatalysis in general is also picking up steam, and looking at in comparison to uranium, which has a natural decay in terms of number of paper per year. But photocatalysis is obviously very, very used, and so I got in early just by luck. So I walked into the wrong seminar room when I first started as a professor, and someone was doing photoredox catalysis. I had never heard of the term, and I just asked a question, and that opened up a whole bunch of collaborations with AstraZeneca, Pfizer, and Merck, where we basically study reaction mechanisms that they develop. And I'll be talking about some of those tomorrow. One of them that I won't be talking about tomorrow is this coupling here, this coupling reaction where you have an iridium, a nickel, and an amine. The amine gets activated and reacts with the nickel. Eventually, will make this nitrogen carbon bond, and it works well. Here's how it works. So this is the the hand wavy explanation for the quantum mechanics behind the photo redox catalysis. So this iridium compound is an iridium-3, a D6 metal. So which means that it has because it's an octahedral field, we'll have, instead of messing up the slide, I'll just use my hands. So when you have a metal in an octahedral field, you'll have that splitting between the EG and T2G orbitals. So the T2G orbitals are the DXY, DYX, DYZ. So those are lower energy. And then you have the orbitals, the D orbitals that really, ram up against the ligand. So the DX squared minus Y squared, that's the one that those electrons, those orbitals are high in energy because they're butting heads with ligands that are also rich in electrons. So you don't want to put electrons where there's already electrons because electrons don't like each other. That's why the dV squared and dx squared minus y squared is higher in energy. Then octahedral field. So you have your dy, dyz, dxz. So these are the ones that are pointing not towards the ligands. And then these are the ones, the EG. So these are, for example, the squared. So these are pointing on the Cartesian axis. And so there's a ligand here with a doublet of electrons. You don't want to put electrons here because that's repulsive. Say when you're dealing with orbitals, in French we call it plein plus plein donne rien. So it's like when it's full and full, the more it rhymes in French. But so the when you have two orbitals that are filled, they don't want to interact. These are filled orbitals, and if you're putting electrons in the dz squared, that's going to be high energy. That's why those energies are much higher. Whereas the dxy, for example, is d, but this is x, y, e. So if it points in between the orbitals, at least it's not putting electrons straight against the ligand. So that's why those are low energy. That's inorganic chemistry. So the iridium is a D6 metal, like that. And then you have a pi star orbital because these are, by design, for electron poor ligands. So the fluorines make the LUMO level lower. So if I erase them, the EG is empty. And the reason why you want to go with iridium is because there's a huge octahedral field. So you're not doing uncontrolled radical chemistry. So that's why iridium is worth so much money because it's rare, but it's also useful. All those metals at the bottom of the periodic table have a huge octahedral field splitting. And so they don't do random radical chemistry like nickel and all. So you have a high octahedral splitting. So now you have this arrangement here, but then the pi star is actually lower in energy than this, or at least it's more accessible. So let me draw somewhere here. So this would be the pi star of your ligand. It's empty. It's an anti-bonding over. If I shine light on this system, you have a transfer of, so it's not a D to G transition. Those are really not allowed. So those mole absorption coefficients are extremely low. So D to D transitions are not allowed. They're forbidden by Laplace. And however, you can do a metal to ligand charge transfer. So metal to ligand charge transfer is allowed, and those can have mole absorption coefficients of 2000 for that molecule. So that molecule will absorb blue light just fine. What happens in terms of the orbitals? The T2G goes to the pi star. Basically, right? So that now you create an excited state. If you have iron can have a EG that's lower energy, and so that excited state won't last very long. So people who are trying to replace iridium for iron are having a hard time because that iron EG is too low, and so you just have mixing very fast and it deactivates and doesn't live long enough. And it's a noteworthy pursuit because iridium is the least abundant metal on Earth. So if you want to do this on large scale, it's not a bad idea to try to use less of it. But you're going to have a hard time if you're doing nickel or iron because either lower in energy and Kasha always wins. Okay, so you have the excited state looks like this. People call it iridium 3 excited state, but really it's an iridium 4. and ligand radical anion. That's really what happens. And then because the iridium is heavy, it goes to the triplets. So spin orbit coupling is very loud, much like I had shown before with the iodine. So when it went from fluorescent to rose bengal, if I put the iodines, all of a sudden it wants to go to the triplets. Same thing with the iridium. So the iridium does spin orbit coupling. Triplet is no problem. Then that molecule, because it's a triplet, it's going to last long. So that excited state will survive for 2.1 microseconds, which is plenty of time to bump into other molecules. And those other molecules could be electron-rich molecules. So a donor, an amine, for example. So that amine will then be able to transfer its electron. It's just downhill. So electrons are always lazy. There's a quote that life is just electrons looking for a place to rest. So there's, light does photosynthesis, excites electron, and those electrons are just looking for places to rest. So they're making chemical reactions. So those electrons here that are high energy from an amine doublet, for example, those are high energy electrons. The other way to think about HOMO orbitals and their energy is like how much do they like protons? So that thing really wants protons. It's a base. So those energies, those electron orbitals are fairly high in energy. Okay, so here I'm going to show you what happens when you add a donor to a. Sure, I can do that. See if it works. Yeah, so if the video works, it's basically going to be the iridium excited state is phosphorescing in this case because it goes through the triplet, so it emits light. And then I'm going to inject amine in there, Radco, so diagonal-based bicycle amine, Radco. That's an amine, and that amine is going to quench the emission of the phosphorescence by electron transfer. Think it works? You see the fluorescence quenching. And so basically, instead of phosphorescing, it does electron transfer. Very efficient. And so that's a very neat demonstration. Probably about $50 for that experiment, but the iridium is very expensive. So now what you have is a donor radical cation and an electron that's weight of too many. So that molecule now is a good electron donor. And that electron is actually in the pi star orbital. So it's no longer, it's not like an iridium 3 excited state, as I said. It's really an iridium 4 ligands electron. So those benzenes here basically have an electron too many. Those are very high energy. And so if you have an acceptor around, that is ready to pick up an electron. And that's it. Now you're back to your photoplatypus. You can do the whole trick again. So in your solution, you have both a good oxidizing and a good reducing agent. And that's why lead is cool, is because you can do, it's difficult to do this with thermal chemistry. If I put lithium aluminum hydride and DDQ, an oxidizing agent, in your flask, they're going to annihilate each other. Whereas here, you can generate them one after the other, so they don't necessarily annihilate each other. That's the beauty of photoredox catalysis. But you can do this also with electrochemistry, because electrochemistry, you have one oxidizing electrode, one reducing electrode. They just happen to be separated physically, but still, the concept is very similar. So everything that's doable photoredox catalysis should be doable electrochemistry. You're basically doing the electrochemistry photochemically when you do photoredox catalysis. So back in 2014, DiRocco at Merck came up with this handy cheat sheet. Basically, it's very hard for you guys to see, I'm sure, but it's just basically looking at all the common photocatalysts and what are the redox potentials of the excited states, of the reduced states, and all that. So I'll show you an example of that iridium. So that compound iridium here, which still doesn't have a name. I don't know if anyone has a name for it. I call it IRB, but it has a really long name. That excited state can oxidize basically anything on the right of this arrow, which means it can oxidize aniline. It does electron transfer just fine, but it can't oxidize a benzene. Benzene will not give an electron to that hole because the redox potentials just don't match up. So that's now in iridium 2, quotation mark, because it's really still iridium 3 pi star radical anion. Now we can look at this side of the chart. So this is again the same molecule. And now we're looking at 1.37, it's very small, but 1.37 means that this molecule, once the iridium picked up an electron, can give an electron to anything that's on the left of this chart. So now it can give an electron to an azide, for example. So the azide will then do nitrogen chemistry and will really mess things up. The nitrogens are pretty reactive. But that's basically it. So that's the chart. So the chart is, you look it up, you say, okay, this excited state. So if I want something that's really, really oxidizing, I go with the triphenylpyrrolium, get oxidized benzene. But that same molecule, if you look over here, can't really turn over with much. You need some sacrificial reducing agent in there, right? Something that's going to be very rich in electron, like a vitamin C or something like that. So that's basically how you can design. It's very difficult to have something that's extremely strongly oxidizing and extremely strongly reducing. Usually it's a window that's moving around. So this is the thermodynamics. So this tells you, could it potentially happen? I prefer kinetics, so we do thermal quenching quite a bit. And so with this same molecule here, just as you saw before, that molecule emits without quencher. As you add quencher, you have a fluorescence decrease. And the fluorescence decrease is related to how quick that reaction is. I'll take time to derive this equation and how we can get these rate constants, if it makes sense. We have a iridium-3 that absorbs light. This is the iridium-3 excited state. From here, a lot of things can happen. There. One is rate constant of K non-rad. This is just heat. So basically you have the iridium-3 plus heat. The other pathway is phosphorescence, K rad. And that one goes back to iridium-3 plus light that we're detecting. And the other one is reaction with a quencher. We have a rate constant for that reaction with a quencher times that. So if we have no quencher, what's going to be the lifetime of this thing? So basically the lifetime is the inverse of all the rate constant pathways. So the lifetime, gotta set it up properly so it works out in the end, but let's do it over here. Stop share so you guys can see the board. Maybe it's gonna work. And then, so this one does electron transfer, iridium-2 in quotation marks plus the radical cation. Trying to figure out how quickly this reaction happens. Is it competing with these ones? So basically the lifetime without quencher is tau 0. So this molecule here, if you excited, let's say if you send a pulse of light, so this would be time. This is the, let's say, amount of excited state. If you send a pulse of laser, you excite that molecule, and then you watch it decay. The lifetime is the average length of time that the molecule survives. It happens to be 1 over E. If this is 1 over E is the lifetime, that would be tau 0. If I add a quencher to this, you'll shorten the lifetime because instead of the excited state having 2 pathways, it now has 3 pathways to get up. So the lifetime will be shorter. How much shorter is related to the rate constant of that electron transfer plus, times the concentration of the quencher. So let's forget about quencher for now. So tau 0 is that's equal to 1 over all the rate constants. I think yeah, okay. So 1 over all the rate constants, which is K non-rad plus K rad. That's a lifetime for without quencher. With quencher, we now have another pathway, which is K non-rad, K rad, plus KQ times concentration of quencher. And when you do thermal quenching, what you're trying to do is the ratio of the emission without quencher and with quencher. And it turns out that the lifetimes is proportional to the fluorescence without quencher and with quencher. And if you derive this, this becomes the denominator, this becomes the denominator. So we have K non-rad plus K rad plus KQ tau, KQ, sorry. And then you basically just, because we're doing tau or tau 0 over tau, this one now becomes like that. K non-rad, K rad, K non-rad. So this becomes 1 plus KQ U, and then 1 over K non-rad, K rad. So this is the rate constant for non-radiative pathway, radiative pathway. That is just a lifetime. That's the definition of lifetime. That becomes Kelvin. So let's see if I got that on my slides. Did I put it? I might not like. But basically, if you do this, if you're measuring the fraction of light that is quenched, your intensity of fluorescence without quencher, with quencher. If the KQ is fast, it's going to quench quite quickly. And if KQ is slow, it's going to quench slowly. It's going to give you a straight line where KQ tau 0 is the slope. If you know tau 0, which is the lifetime of the excited state, then you can measure KQ. And we've done that for a bunch of molecules. So we see here electron-rich amines quench very quickly. Electron-poor amines like pyridine quench very slowly. And that, I think, makes intuitive sense. I think most people will put those molecules in there. But some molecules are a little bit trickier. Phenols also quench quite well. We measured it with a bunch of different molecules. But now we can have a model that's predicting. So if you plot the rate constant of quenching versus the ionization energy, and we rework from this paper now with Marcus theory, which should tighten up the correlation. So Marcus theory is a way to predict rate constants for electron transfer. But yeah, so basically this is good enough to predict reagents. For example, ACAC is not a good quencher at all. But if you deprotonate it, all of a sudden it becomes fine. It reacts at 10 to the 8. So actually you can react ACAC in slightly basic conditions and get these weird products here in 100% yield, because all of a sudden you become a little electron acceptor. So it's a way of making carbon-centered radicals. There are other molecules like this one. So B2PIN2 is not a good electron donor. But if you do it in base media, all of a sudden it becomes an excellent electron donor. It reacts so fast that we could do this chemistry reaction with copper, which is not a great oxidizing agent. But it was actually, that copper was able to oxidize this B2PIN2 anion and could then cleave that boron bond, make boron-centered radicals, which would then add to triple bonds and do a chain reaction like this with the fairly high quantum yield. And also we could prove that there were boron-centered radicals because we could trap them by mass. So this is done in collaboration with Thomas Poisson in France at Rouen. Okay, so iridium, as I said, is very expensive. So this is coming up the home stretch. Iridium is very expensive, the least abundant metal on Earth. And so people who do iridium chemistry then go with 4-CzIPM. So why this molecule? Well, it turns out that the excited state lifetime is decent, that the redox potential of that molecule are close to that of the iridium. So it's fairly easy to try and swap them out. Usually you'll get slightly better yields with this one, but it's way cheaper with this molecule. So let's go and understand why that works. It works because it goes to the triplet. It's not trivial to have a molecule that doesn't have a bunch of iodines around or a bunch of heavy metals around to go to the triplet. But this molecule here is able to do so. And I'll try to explain to you why. So a lot of the experiments that we do is something called laser flash photolysis, where we pulse a sample with a laser and we measure transient absorption. So basically we measure the sample's absorption a few nanoseconds after the laser hits. And then we follow that absorption over time. So that molecule starts in the ground state as 0. We excite it with a 355 laser, and it goes to some higher excited state and quickly goes to S1. S1 DV. That's cash over. So we see a negative absorbance. A negative absorbance because the ground state is gone. So the molecule previously was yellow, it absorbed blue light. Now it's in the excited state, so it's no longer there to absorb. So that's why we have negative absorbance. It also quickly goes to the intersystem crossing. So it goes to the intersystem crossing quickly because the electrons are doing their parkour thing, because the S1 and T1 are very close in energy. And I'll explain to you why that is in this case, in this molecule. That actually goes to the triplet. We can observe that triplet here a little bit. We can actually observe delayed fluorescence as well. So these are thermally activated delayed fluorescence molecules. So just with heat, we can have triplets that go over the barrier and equilibrate. So we continuously see fluorescence from this molecule, but that fluorescence has the same lifetime as the triplet. That triplet lives. Eventually, we'll go see what's going on in the singlet, and it will drop down in a minute photon. And then some more triplet will do that, and we measure the lifetime of all these processes, and they're all the same. So the ground state recovery, the triplet bleaching, the delayed fluorescence, they all have the same decay rate constant. They all have the same life. So that molecule lives 1.6 microseconds, and it has time to do chemistry, basically. But the reason why it's so it's able to do the singlet triplet transfer is because the gap is small. Why is the gap is small? Is because the orbitals HOMO and LUMO don't occupy the same space. So imagine two methyl radicals. We have a methyl radical that is separated from another methyl radical by a meter. What do you think is the singlet triplet gap of that? So those two electrons are like this or like that. The singlet triplet gap is 0. There's no advantage of being a triplet. However, if you're an ethane, the singlet triplet gap is huge, right? Because you're going from a bonding to an anti-bonding orbital. So it turns out that triplets have a natural tendency to avoid each other. So you have two electrons that have the same spin, they cannot occupy the same space. And that's good. Imagine you had a roommate that can never walk in the room that you're in. That probably would lower your energy, would make it so that, especially if you don't like your roommate like electrons do, right? Electrons don't like each other. So if you have two electrons that have the same spin, the fact that they can't occupy the same space is great for them. It's stabilizing. So in this case, it doesn't have that stabilizing energy. So that singlet triplet gap now becomes quite small because there's no really huge advantage of being singlet or triplet because they don't actually occupy the same space. So the advantage of being a triplet and having this natural tendency of not occupying the same space is no longer an advantage. They're living in completely different buildings, and so it doesn't matter. So this molecule has electron-rich carbozoles, electron-poor cyano center, and so we have a charge transfer intraband, and so now it becomes quite simple to do the spin flip. And also, these are useful for lighting diodes because when you're passing a current through these tiny things, those electrons can recombine in same spin, opposite spin. So the fact that they can go to the triplet and still emit actually increases the amount of light that you have out. For those that caught that wave, it's a pretty cool design for that as well. So that's basically it. So I showed you some photochemistry, but I wanted to do a small demo at the end. So let's do that. Are there questions before I do the small demo? I'm sure there are, but so I just went rapid fire, just trying to give as much information in 2 hours as I could. And then I was told at some point that you want to end on some joke or something that's fun for a presentation because then people leave thinking that they had fun the whole time. It's do something that's fun, hopefully. Some of you might be a little burned from all the photons. Okay, so the demonstration is something at model level training. This is fluorescent diacetate in here and KOH. So basically, I'm going to take this molecule, which is a live cell assay molecule. So fluorescent diacetate is apolar, can go through the cell membrane. And once it goes in the cell membrane, can recombine or can get esterase, so react with esterases. Those esterases will make your alcohols, and those alcohols will open up the lactone, and you'll go from an sp3 carbon where nothing talks to nothing to an sp2 carbon where things start to delocalize. All of a sudden, the particle in the box is, the levels get smaller, they get closer in energy. So rather than absorbing UV, they start absorbing in the visible. Now this molecule now can emit the light. So basically, we'll do that small demonstration right now with that fluorescent acetate. So after you need some mystery liquid, is ethanol, ethanol and Erlenmeyer. Yeah, so I'll start with the setup and then we'll turn off the light just for the actual demo. So I should be able to, so this is just ethanol. I should be able to add just a little bit. So this is my fluorescent diacetate. Have a little bit in there. And maybe if I can get a volunteer to help me with these flashlights, actually can lift them up. So basically you're going to point this not at my eyes, but at the solution. I'll try to hold it like this so you can see. And then something that's fun as well. Can I get one more volunteer to hold this while I valves? Yeah, I will turn them off in a minute. So let me do that. Okay. There's something that's fun. So okay. It's not that bad. It's a UVA light. Yeah. Oh, actually, yeah, there we go. You can see. Okay, so now I have so the reaction is this, which you can't really see very well. But if I turn on black light, you'll see it quite well. So the highlighters are fluorescent. That's why they look weird. And also paper is fluorescent. So now your good paper is useful because it has a lot of fluorescent dyes in it. Those fluorescent dyes in the paper make paper more white than white. So basically they take UV light that we don't see and convert it to blue light to counteract the yellowing of paper. So there's a lot of chemistry in paper. There's dyes that prevent photo bleaching, but also those dyes absorb the light and convert it to blue light so it becomes whiter than white paper. So we have a fluorescent here that's crudely drawn, but you can see it on the screen a bit better. That will react with the KOH, so I have KOH in the pellet form, and it should open up the lactone and become fluorescent. So for that, we'll do it in the dark. One more volunteer to close the, okay, there we go. Close the lights. Yeah. Here, you can have goggles. If someone takes a picture, at least I'm the one not wearing goggles. Oh, okay. Now that's go. Yeah. Lower the light intensity here. Okay, so
Keep it out of bounds. Thank you.
okay, so I have KOH. I'm gonna drop the pellets in, and then so what's gonna happen is there's gonna be hydrolysis where the KOH dissolves. Works. You can also see my closed fluorescence. The way to see if there's stains. If those stains absorb, it will allow fluorescence. Okay, here goes the demo. Coming in. One. Nope, that's probably fine. Okay, we can see that one starting fluorescence. We can start to see the fluorescence coming off of the KOH dissolving of the fluorescent diacetate. The fluorescent diacetate is being converted into fluorescent. And slowly the KOH is dissolving, but you see it's heavier. So it actually stays at the bottom. And then if I do 3, 2, 1, we'll be able to see the fluorescence quite a bit. And that's my share. Thank you. Right there. Right here, lad. All right. So I think the room's taken out at 4:30, so we have to leave soon. But I'm giving a talk tomorrow. 10 or 11. 10. So okay, then we'll be talking about. So this will be the basis to understand some of that tomorrow. Right. So thank you very much for coming, and I can hang outside if there are questions. Thank you.